Similar to protein interface prediction, there is another application called drug-drug interaction prediction. What does it mean by drug-drug interaction and why we are interested in it? Certain diseases are complex diseases. It requires multiple drugs to treat the diseases. For example, in certain cases, we need to take a cocktail of drugs because they are complex in nature. Sometimes patient itself have a multiple diseases. For example, they have a high blood pressure or they have a diabetes and they have to take a drug for a high blood pressure, they have to take a drug for diabetes. So often the diseases are complex or a patient have multiple diseases, and hence there is a requirement of taking a multiple drugs. Now, when we take multiple drugs to treat a patient, it is called polypharmacy. And in a polypharmacy, one of the major challenge is side effect of two drugs. When you take two drugs together, they interact and create a side effect. And that's why polypharmacy is often considered to be risky. And if we do not know that whether these two drugs interact and the patient goes through those treatment, it may have a very poor effect on patient's health. Hence, we want to know whether two drugs taken together has a side effect or not, or whether these two drugs interact or not. And this is called drug-drug interaction problem. It is important to predict the side effect of a pair of drugs. And if we can predict it whether it is a severe, mild, or no effect, we can actually recommend patient or practitioner to advise to take these two drugs together. Now, if we look at this particular problem, we can think of each of this drug as a molecular graph, and drug 1 it can be modeled as a graph 1 with a GD1, denoted as GD1, with a set of vertices or node VD1 and set of edges ED1. Similarly, drug 2 can consider as the graph GD2 with vertices VD2 and edge ED2. Now, if you can see that drug 1 is modeled as a graph, drug 2 is modeled as a graph, then do you get any idea from the protein interface prediction task? Yes, we can do something about it. There are certain similarity, there are certain differences. We'll see what are those. The task here is, given two drugs, we want to predict whether they interact or not. Sometimes there is a multi-class problem which we also look at, is given two drugs, whether they interact mildly, medium, or severely. Okay, so in that case, you have a 3-class problem or 4-class problem if you say they do not interact at all. However, for this particular lecture, we'll keep it as a 2-class problem. Remember that whether it is a 2-class problem or multi-class problem, the procedure is not going to change. Only the label is going to change. In other words, given data, let's say I have a pair of GDI, GDJ drugs, then question is whether it is a 2-class problem or it is a multi-class problem. the first part, where we look at the interaction between two drugs, is going to remain same. The later part, once we generate the feature for the pairs, is going to change. Okay, because there one place we have a binary classification problem, in other case we have a multi-class classification problem. So let's look at it. As I told you, it is similar to protein interface prediction, but it's a graph level embedding. Recall, in a protein interface prediction, we have looked at the node level embedding. We refined the node features. We have not refined graph level features. We are going to define here graph level representation using node features, of course, but unlike the protein interface prediction task, we are not going to stop at defining the node features or learning the node features. We are going to also learn graph level embedding. So we are going to use pooling operations in this particular case. So here we have a graph associated with molecule 1 and graph associated with molecule 2. Here you can see that we have two different kind of molecules, and hence the molecular graphs are different. Also, the node features are also different because we have a different node here. Or node has a different characteristic, it can be different atom. And what we are interested in here is take these two molecular graph and learn feature representation of this molecular graph. So we are going to pass through them through graph neural network 1, graph neural network 2. So both of them pass through the graph neural networks. How to learn them together? You can learn for representation of each graph independently using all the unlabeled data, like as we discussed earlier in molecular property prediction, or you can actually combine with the task of interest or downstream task of interest. But here what I have done is use the unlabeled approach to learn the graph neural networks. In that case, there are certain properties such as Laplacian between the reconstructed graph and the input graph can be minimized, etc. Having said that, we learn graph representation for G1, which is defined as a FGD1, and graph representation for molecule GD2, which is FGD2. So I have two graph level representation embedding. Now what I'm going to do is I'm going to take this FGD1 and FGD2 together to construct a embedding through a merging operation. This merging operation again can be some kind of pooling operations or just concatenation of two features vector. Once I have now feature for the GD1, GD2 pair. A pair of two drugs feature has been constructed, and then I can again go back to fully connected layers or feed for neural networks to perform a classification task. As I mentioned, this particular downstream task can be decoupled from the upstream task of learning the features. Hence, here I can use unlabeled data So all the molecules available to me, drug molecules, I can use them together to develop graph neural networks, which can provide me a best graph representation for different molecules. Once I have this, I can go back here and use labeled data where for each pair of molecule I have a label associated with it, either 0 or 1. So I can use this to actually train this neural network model, and then for a new pair of drugs, what I will do is following. I'll first take it to the graph neural networks, learn the embedding, get embedding for both of them, and use this learned fully connected neural layer to actually predict the class. So this way we can actually do the drug-drug interactions. Another application which is of quite interest to many drug discovery and design tasks is a drug target binding affinity prediction. As we discussed, a new drug development is time consuming and costly. And if we can actually the next task we are going to look at is a drug target binding affinity prediction. We already learned that new drug development is time consuming and costly, and drug target interactions has a very interesting application in terms of narrowing down the search space for the candidate drugs. That's one advantage. It will actually narrow down what are the candidate drugs we should search for in the universe of all the possibility in the drugs. Another interesting application which has been there for a while but has been used widely last 2 decades is a drug repurposing. Often we have existing regulatory approved drug, and we ask the question, will this existing drug have an effect on new diseases, or it can cure some other diseases, or some abandoned drugs, those drugs which could not clear the clinical trial. Can I actually identify new targets for them so that they may not be useful in one disease, but they may be useful in other disease? This is called drug repurposing, where aim is to identify new targets for the existing or abandoned drugs. If we can do that, then we can actually discover a new drug using new drug for or we can say existing drug for a new disease, or abandoned drugs for a new disease. And drug target binding affinity prediction help us to do faster, not only drug search, but also drug repurposing. It try to figure it out or infer the strength of binding between a given drug and a target. Here the targets can be a protein, so drug target interactions, targets can be anything. We are looking for drugs interaction with particular protein, or drugs interaction in certain disease or gene, or in some cases side effects. So I also want to, like in previous case we discussed, drug-drug interactions is also a subset of problem or drug-target interactions. However, in this particular example, we will look at little bit of variation of drug interaction problem, where we look at protein drug interactions. However, the method can be applied to drug disease, drug gene, and side effect also. So how we are going to actually perform a drug target binding affinity prediction task? First, we have to actually get models for drug and target. Remember, drugs are nothing but a small molecules, so we can always represent them as a graph. So I'm representing drug as a graph GD1, where VD1 is a set of nodes and ED1 is set of edges. And we can use all the definition of nodes and edges which we have used for molecular property prediction, drug-drug interactions, to actually create a graph for the drug. In case of protein, it can be models as a graph with the same definition which we use for the protein interface prediction, or we can use protein or model protein as a sequence of amino acids. In this case, we will consider protein as a sequence of amino acids or a sequential data. And to model sequential data, there are many other models available in the literatures which you must have studied, like LSTM, RNN, etc. Here, for the sake of variety, we will assume that instead of graph representation of protein, we will assume sequence of amino representation of protein. But drug will be graph. And now, what I'm interested in is, I want to infer the drug and protein binding affinity using the available data. Since I'm only interested in whether the particular drug and target has a binding affinity or not, it is again modeled as a binary classification problem. You can also predict the affinity level in terms of regression. So in that case, it will be a regression problem. However, I'm not quantifying it. I'm just predicting whether there is a sufficient binding affinity between drug and given target is there or not. As I told you, it is similar to drug-drug interactions. Only difference here is that in the case of drug, we have a molecular graph. In case of protein, we are taking a sequence of amino acid as a model. So we are taking it is graph to sequence interactions we are looking for. And as I told you, why we can take a sequence, because protein is a sequence and the sequence models are often used for embedding the proteins. Hence, we can actually use those models in this particular task. So let's look at this particular task. We have a drug GD1, and as we know, we can represent as a graph with a node and the corresponding feature. And I have taken a protein as a sequence of amino acids. And what I'm going to do is I'm going to pass this drug molecule through graph neural network. While in the case of protein, I'm going to use sequence models like LSTM, RNN to generate a feature for drug GD1 and feature for the protein sequence P. So I have a feature for protein sequence here, and I have feature for graph. Now, like in a drug-drug interactions, we perform a concatenation operation and generate the feature for graph protein pair. Using this feature, I can actually train fully connected layer to perform a classification task. Here we can actually perform this operation separately than this operation, or we can combine depending on the complexity of the problem. Again, you can see that this is the same level task what we have seen for the drug-drug interaction task. Unlike merging operation, where merging operation can be done indifferently, concatenation is a commonly done operation when we want to merge two features and create a global features for interactions. So these are the applications of graph neural networks in drug discovery and design, where we either look for only one graph, like a molecular property prediction graph, or we have two entities, like a drug-drug interaction graphs, or we have one molecular graph and other one as a model as a sequence graph, and still we can actually perform some kind of predictions, for example, in case of drug target binding affinity predictions. So with this, we end with the application to drug discovery.